Hello 10th class students. As FA2 is approaching in the 15th week, we are now currently into the 15th week. The syllabus for the 10th class is chapter 3 and chapter 4. Chapter 3 is acids, bases and salts, and chapter 4 is your refraction of light at curved surfaces. So you'll get the videos, revision videos regarding that. The first part will be again an animated version. The second part in the revision week will be again an animated version. And third part, fourth part will be my explanation for question and answers, which you'll get in your FA2 examination. So watch them thoroughly and be prepared for the FA2 exam which is being conducted in this current week.
Refraction of light at curved surface. We already discussed about refraction of light at plane surface. Now we know about the refraction of light at curved surface. It is a common observation that some people use spectacles for reading. The watch repairer activity. Draw an arrow of length 4 cm using a black sketch pen on a thick sheet of paper. Take an empty cylindrical shaped transparent vessel. Keep it on the table. Ask your friend to bring the sheet of paper on which arrow was drawn behind the vessel while you look at it from the other side. We will activity. Draw an arrow of length 4 cm using a black sketch pen on a thick sheet of paper. Take an empty cylindrical shaped transparent vessel. Keep it on the table. Ask your friend to bring the sheet of paper on which arrow was drawn behind the vessel while you look at it from the other side. We will see a diminished image of the arrow. Ask your friend to fill vessel with water. Look at the arrow from the same position as before. We can observe the inverted image. Explanation. At the first time, light travels through two media, that is, glass and air comes out of the vessel. So, it forms an inverted image. For example, the refractive index of glass and water are the same. This setup of air, water separated by a curved surface is shown in figure. What happens when a ray of light incident on a curved surface separating the two media? Are the laws of refraction still valid? Let us find out. Consider a curved surface separating two different media as shown in figure. The center of the sphere, of which curved surface is a part, is called as center of curvature. It is denoted by letter C. Any line drawn from the center of curvature to a point on the curved surface becomes normal to the curved surface at that point. The direction of the normal changes from one point to another point on the curved surface. The center of the curved surface is called the pole P of the curved surface. The line that joins the center of curvature and the pole is called principal axis. Let us see how we can draw array diagrams for certain useful cases. We know that a normal drawn to any point on a curved surface passes through center. We incident or pass the light ray in such a way it makes an angle 0 degree with normal, it remains in same path or undeviate its path. According to Snell's law, let us see how we can draw array diagrams for certain useful cases. We know that a normal drawn to any point on a curved surface passes through center. We incident or pass the light ray in such a way it makes an angle 0 degree with normal, it remains in same path or undeviate its path. According to Snell's law, the ray which travels along the normal drawn to the surface not deviate its path. Observe the figure Case 1. A ray traveling parallel to the principal axis strikes a convex surface and passes from the rarer medium to denser medium. Case 2. A ray traveling parallel to the principal axis strikes a convex surface and passes from the denser medium to rarer medium. Case 3. A ray traveling parallel to the principal axis strikes a concave surface and passes from the denser medium to rarer medium. Case 4. A ray traveling parallel to the principal axis strikes a concave surface and passes from a rarer medium to denser medium. What differences do you notice in the refracted rays? What differences do you notice refracted rays? What could be the reason for those differences? You might have noticed that the refracted ray reaches a particular point, image formation. Consider a curved surface which separated the two media of refractive indices n1 and n2. A point object is placed on the principal axis at point O. The ray which travels along the principal axis passes through the pole undeviated. The second ray, which forms an angle with a image formation. Consider a curved surface which separated the two media of refractive indices n1 and n2. A point object is placed on the principal axis at point O. The ray which travels along the principal axis passes through the pole undeviated. The second ray, which forms an angle with a principal axis, meets the interface at A. The angle of incidence is θ1. The ray bends and passes through the second medium along the lane AI. The angle of refraction is θ2. The two refracted rays meet at I and the image is formed there. Let the angle made by the second refracted ray with principal axis be gamma and the angle between the normal and principal axis be beta. From figure, PO equals to U object distance, PI equals to B image distance, PC equals to R radius of curvature, and N1, N2 are refractive indices of the media. From triangle ACO, θ1 equals to alpha plus beta. Triangle ACI, beta equals to θ2 plus gamma, which implies θ2 equals to beta minus gamma. According to Snell's law, n1 sin θ1 equals to n2 sin theta. Therefore, n1 sin alpha plus beta equals to n2 sin beta minus gamma. Let this be equation 1. As per paraxial approximation, sin alpha plus beta equals to alpha plus beta and sin into beta minus gamma equals to beta minus gamma, which implies n1 into alpha plus beta equals to n2 into beta minus gamma, which implies n1 alpha plus n1 beta equals to n2 beta minus n2 gamma. Let this be equation 2. Since all angles are small, we can write tan alpha equals to an by no equals to alpha, tan beta equals to an by nc equals to beta, tan gamma equals to an by ni equals to gamma, which implies n1 into an by no plus n1 into an by nc equals to n2 into an by nc minus n2 into an by ni. Let this be equation 3. As the rays are very close the principal axis, the point N coincides with P. NO equals to PO, NI equals to PI, NC equals to PC. This implies N1 by PO plus N1 by PC equals to N2 by PC minus N2 by PI, which implies N1 by PO plus N2 by PI equals to N2 minus N1 by PC. Let this be equation 4. Using sign convention, PO equals to minus U, PI equals to P, PC equals to R. This implies N1 by minus U plus N2 by P equals to N2 minus. Example: a bird is flying down vertically towards the surface of water present in a pond with a constant speed. The fish inside the water is exactly vertically below the bird. Then the bird will appear to fish B further away than its actual distance, closer than its actual distance, moving faster. Example: a bird is flying down vertically towards the surface of water present in a pond with a constant speed. The fish inside the water is exactly vertically below the bird. Then the bird will appear to fish B further away than its actual distance, closer than its actual distance, moving faster than its actual speed, moving slower than its actual speed. Which of the four options is true? How can you prove it? Solution: for refraction at a plane surface, we use N2 by V equals to N1 by U. Let this be equation 1. Let x be the height of the bird above the water surface at an instant, and n be the refractive index of water. N1 equals to refractive index of air. Then N1 equals to 1, N2 equals to n, U equals to minus x, and let V equals to minus pi. Substituting these values in equation 1, n by minus y equals to 1 by minus x, which implies y equals to nx. In the above equation, we know that n is greater than 1. Hence, y is greater than x. Thus, the bird appears to the example. A transparent sphere of radius r and refractive index n is kept in air. What distance from the surface of a sphere should a point of object be placed on the principal axis so as to form a real image at the same distance from the surface of sphere? Solution: U equals. Example: a transparent sphere of radius r and refractive index n is kept in air. What distance from the surface of a sphere should a point of object be placed on the principal axis so as to form a real image at the same distance from the surface of sphere? Solution: U equals to minus x, V equals to alpha, because the refracted ray are parallel to principal axis. After refracting the first surface, n1 equals to 1, n2 equals to n, n2 by v minus n1 by u equals to n2 minus n1 by r. N by alpha minus 1 by minus x equals to n minus 1 by r. 1 by x equals to n minus 1 by r. X equals to r by n minus 1. Object distance from the first surface of the sphere is x equals to r by n minus 1. Up to now, we have discussed about the refraction of light through lenses. A plane transparent medium is bounded by two surfaces, at least one of them is spherical. That is, a lens is bounded by at least one curved surface. Depending upon the shape of the surfaces, lens can be of different types. Double convex lens. A lens is formed with two bulging out surfaces is called lenses. A plain transparent medium is bounded by two surfaces, at least one of them is spherical. That is, a lens is bounded by at least one curved surface. Depending upon the shape of the surfaces, lens can be of different types. Double convex lens. A lens is formed with two bulging out surfaces is called a convex lens. It is thicker in the middle, thinner at the edges. Double concave lens. A lens is formed by two spherical surfaces. Those are bulging in surfaces curved inwards is called a double concave lens. It is thinner in the middle, thicker to the edges. Plano concave lens. Among two surfaces, one is plane and the other is concave surfaces called as plano concave lens. Plano convex lens. A lens is formed by two surfaces. Among the two surfaces, one is convex and the other is a plane, is called a plano convex lens. Concavo convex lens. While calling the name of the lens, the name of the surface having more radius of the name of lens, the name of curvature, we call the name of lens, the name of surface as first a concavo convex lens having two refracting surfaces, one is concave and the other is convex. Here we are concerned only with thin lenses, that is, the thickness of the lens is negligible. Let us learn the terminology used in the case of lenses. Each curved surface of lens is part of the sphere. The center of the sphere, which contains the part of the curved surface, is called center of curvature. It is denoted by letter C. If a lens contains two curved surfaces, then their centers of curvature are denoted as C1 and C2. The distance between the center of curvature and curved surface is called radius of curvature. Radii of curvature are represented by R1 and R2 respectively. Let us consider a double convex lens as shown in the figure. The line joining the points C1 and C2 is called principal axis. The midpoint of a thin lens is called optic center of lens P. Focal length of the lens. A parallel beam of light rays incident or a lens after refraction converges at a point on the principal axis. The point from which the rays seem to emanate is called a focal point or focus. The distance between the focal point and the optical center is called the focal length. For drawing the ray diagram of lenses, we can represent the convex lens with a symbol and concave lens. Does the lens form an image? How does it form an image? To know the formation of image by lenses, we need to know the behavior of light rays when they are passing through the lens. We know that the lens has two surfaces while drawing a ray diagram. We cut the lens at a single surface because we assume that the thickness of the lens is very small and the net refraction at only one of the surfaces. Behavior of certain rays when they are incident on the lens. Case 1. A ray of light passing along the principal axis remains undeviated. Case 2. A ray passing through the optical center is also undeviated. Case 3. A ray passing parallel to the principal axis after refracting the light rays converging a point on the principal axis or appeared to diverge from focus. Case 4. The ray passing through the focus will take a path parallel to principal axis after refraction. If we incident the ray of the lights in such a way that it passes through focus, Rays obey the principle of least time after refraction passes parallel to the principal axis. Rules to draw ray diagrams for image formation by lenses. Let us learn a few basic rules to draw ray diagrams to locate the position of images. For drawing a ray diagram to find position and size of the image formed by the lens for any position of object on the principal axis, you need to follow the rules mentioned below. For locating position and to find the size of image, we need 2 rays out of 4 rays that were mentioned in the situations 1 to 4. Select a point on the object placed at the point on the principal axis. Draw 2 rays that were chosen by you from rays mentioned in situations 1 to 4. Extend both rays to intersect at a point. This point gives position of the image. Draw a normal from point of intersection to the principal axis. Length of this normal represents the size of the image. Observe the following diagrams. They represent image formation of a convex lens for various positions of the object. Object at infinity. What do you mean by the object at infinity? What type of rays fall on the lens? You know that the rays falling on the lens from an object at infinity are parallel to the principal axis. They converge to the focal point. So, a point-sized image is formed at the focal point. This can be seen. Object placed beyond the center of curvature on the principal axis. When object is placed beyond the center of curvature, C2, a real, inverted and diminished image is formed on the principal axis between the points F1 and C1. We have chosen 2 rays, one ray passing parallel to the principal axis and another ray passing through the optic center to locate the position of the image. Try to draw ray diagram using the pair of rays, one passing parallel to the axis, another passing through the focus. Object placed at the center of curvature. When an object is placed at the center of curvature, C2, on the principal axis, you will get an image at C1 which is real, inverted and of the same size as that of object. Object placed between the center of curvature and focal point. When an object is placed between center of curvature C2 and focus F2, you will get an image which is real, inverted and magnified. The image will form beyond C1. Object located at the focal point. When an object is placed at focus F2, the image will be at infinity. When the image is formed at the infinity distance way, we cannot discuss the size and nature of the image. Object placed between focal point and optic center. If we place an object between focus and optic center, we will get an image which is virtual, erect and magnified. From the ray diagram, you will notice that the image formed is a virtual, erect and is formed on the same side of the lens where the object is placed. The size of the image is lesser than that of the object. It is a magnified image. In the above situation of image formation, we understand 2 things. As the image formed is virtual, we can see it with our eyes. In all other cases, the image is real, which we cannot see with our eyes, but can be viewed if the image is captured on a screen. a magnified virtual image is formed on the same side of the lens where the object is placed. Thus, the image you are seeing through a lens is not real. It is a virtual image of the object. This particular behavior of convex lens helps to construct a microscope which gives a magnified image. You might remember that the magnification of the virtual image is possible only when the object is at the distance less than the focal length of the lens. Till now, we have drawn ray diagrams for various positions of object placed on a principal axis using convex lens. Draw ray diagram for an object placing between C1 and F1 for a concave lens. What do you notice? Verify your ray diagram with the ray diagram we have drawn for a convex lens. Try to draw ray diagrams for other positions of an object. You will notice that irrespective of the position of object on the principal axis, you will get an erect virtual image diminishing in size in between the focal point and optic center for concave lens. Let us see a few examples of ray diagrams. Example: draw a ray diagram to locate the position of image when a point source S is placed on the optical axis M and of a convex lens in such a way that it is beyond focal point F. Solution: draw a perpendicular line to principal axis passing through the focus F dash. Draw a ray from point source S in any direction to meet lens at point P dash. Now, draw another line parallel to the ray diagram from the point source S such that it passes through the optic center P. This line intersects the normal at point F4. Now, draw a line passing from point P dash to pass through the point F4 such that it meets principal axis at the point say I. I is the image point for the point source S. Example: complete the ray diagram to show the path of the rays after refraction through the lenses shown. Solution: follow the steps mentioned in previous examples to complete the ray diagrams. You will notice that the paths of the rays are shown. Can we realize in practice the results obtained in the ray diagrams when we perform experiments with a lens? Activity. Procedure: take a V stand and place a convex lens on this stand. Imagine the principal axis of the lens. Light a candle and ask your friend to take the candle far away from the lens along the principal axis. We use a screen because it forms a real image generally which will form a screen. Real images cannot be seen with an eye. Adjust the screen on other side of lens until clear image form on it. Measure the distance of the image from the stand and also measure the distance between the candle and stand of lens. Now place the candle at the distance of 60 cm from the lens, such as the flame of the candle lies on the principal axis of the lens. Try to get an image of candle flame on the other side on the screen. Adjust the screen till you get a clear image. Measure the distance of image U from lens and record the value of U and V in the table. Repeat this for various distances of image. In all cases, note it in the table. Observations: object distance, image distance, focal length, Characteristics of image: 60 centimeter, 60 centimeter, 30 centimeter, same size real, inverted, 50 centimeter, 75 centimeter, 30 centimeter, enlarged, real, inverted, 40 centimeters, 120 centimeters, 30 centimeters, enlarged, real, inverted, 30 centimeters, infinity, 30 centimeters, highly enlarged, real, inverted, 20 centimeters, 60 centimeters, 30 centimeters, enlarged, virtual, erect. Conclusion: from this, we conclude that a convex lens forms both real and virtual image when object placed at various positions. Could you get an image on the screen for every object distance? No. Why do not you get an image for certain object distance? Because the lens not always forms real image, so real image only be got on screen. What do you observe? Do you find the minimum limiting object distance for obtaining real image? What do you call the minimum limited object distance for real image? When the object is placed at f, that is the distance between the object and lens is not less than the focal length of that lens, then you observe the real image on screen. When you do not get an image on the screen, when the object is placed in between focus and optical center of the lens, you could not observe the image of the object on the screen. It indicates that what stage the formed image is not real. You will see a virtual magnified image on the same side where we kept an object. Can we find the object distance? Is considered an object distance is u and image distance v and the focal length f. Can we establish any relation between u, v and f? Let us find out. Lens formula. Consider an object O, O dash placed on the principal axis in front of the convex lens. Let I dash be the real image formed on the other side of it. How is the image formed? From the figure, PO, PI, PF1 are the object distance, image distance and focal length respectively. Triangle P, P dash, F1, triangle F1, I dash implies P, P dash by I dash equals to PF1 by F1I. Let this be equation 1. From the figure, F1I equals to Pi minus Pf1. Therefore, equation 1 implies P dash by I dash equals to Pf1 by Pi minus F1. Let this be equation 2. Triangle O dash P, triangle Pi dash, which implies O dash by I dash equals to Po by Pi. From the figure, O dash equals to P dash, which implies P dash by I dash equals to Po by Pi. Let this be equation 3. From equation 2 and 3, Pf1 by Pi minus Pf1 equals to Po by Pi, which implies Pi by by PO equals to PI minus PF1 by PF1, which implies PI by PO equals to PI by PF1 minus 1. Divide both sides by PI, which implies 1 by PO equals to 1 by PF1 minus 1 by PI. 1 by PO plus 1 by PI equals to 1 by PF1. This is for convex lens. To generalize, we have to use sign convention, which implies PO equals to minus U, PI equals to V, PF1 equals to F, which implies 1 by V minus 1 by U equals to 1 by F. Therefore, this is called lens formula. Example: an electric lamp and a screen are placed on the table in a line at a distance of 1 meter. In what positions of convex lens of focal length of f equals to 21 centimeter will the image of lamp be sharp? Solution: let d be the distance between the lamp and screen and x be the distance between lamp and lens. From figure, we have u equals to minus x and v equals to d minus x. By substituting these in lens formula, we get 1 by f equals to 1 by d minus x plus 1 by x. After solving this equation, we get x square minus dx plus fd equals to 0. It is a quadratic equation. Hence, we get two solutions. The solutions of the above equation are x equals to d plus or minus root of d square minus 4fd by 2. Let this be equation 1. Given that f equals to 21 centimeter and d equals to 1 meter equals to 100 centimeter. Substituting these values in equation 1, we get x1 equals to 70 centimeter and x2 equals to 30 centimeter. Note: image of the lamp can be sharp only when f is less than or equal to 25 centimeter. Discuss the reason for this using equation 1. Take the help of your teacher. Activity: take a cylindrical vessel such as a glass tumbler whose height must be nearly 4 times of the focal length of the lens. Keep a black stone inside the vessel at its bottom. Now pour water into the vessel up to a height such that the height of the water level from the top of the stone is greater than focal length of the lens. Now dip the lens horizontally using a circular lens holder as shown in the figure. Set the distance between stone and lens, that is equal to or less than focal length of lens. Now look at the stone through the lens. We can see the image of the stone if the distance between lens and stone is less than the focal length of the lens. Now increase the distance between lens and stone until you cannot see the image of the stone. We have dipped the lens to a certain height which is greater than the focal length of the lens in air, but we can see the image. This shows that the focal length of lens has increased in water. Lens maker's formula: image a point object O placed on the principal axis of the thin lens. Let this lens be placed in a medium of refractive index Na and let the refractive index of lens medium be Nb. Consider a ray from O which is incident on the convex surface of the lens with radius of curvature r1 at A as shown in the figure. the incident ray refracted at A. Let us assume that it forms image at Q if there were no concave surface. From figure VO equals to minus U, PQ equals to P, which is equals to X. Radius of curvature R equals to R1, NA equals to N1 and N2 equals to NB. Substitute the above values is N2 by V minus N1 by U equals to N2 minus N1 by R1, which implies NB by X plus NA by U equals to NB minus NA by R1. Let this be equation 1. But the ray that has refracted at A suffers another refraction at B on the concave surface with radius of curvature R2. At B, the ray is refracted and reaches I on the principal axis. The image Q of the object due to the convex surface is taken as object for the concave surface. So, we can say that I is the image of Q for concave surface. Object distance U equals to PQ equals to plus X. Image distance PI equals to V. Radius of curvature R equals to minus R2. N1 equals to NB and N2 equals to NA. Substitute the above values in N2 by V minus N1 by U equals to N2 minus N1 by R. NA by V minus NB by X equals to NB minus NA by minus R2. Let this be equation 2. Add equation 1 and 2. NA by V plus NA by U equals to NB minus NA into 1 by R1 plus 1 by R2. Divide both sides with NA. 1 by V plus 1 by U equals to NB by NA minus 1 into 1 by R1 plus 1 by R2. NB by NA equals to NBA, called refractive index of lens with respect to surrounding medium. 1 by V plus 1 by U equals to NBA minus 1 into 1 by R1 plus 1 by R2. This is for convex lens. To generalize, we use sign convention. 1 by V minus 1 by U equals to NBA minus 1 into 1 by R1 minus 1 by R2. 1 by V minus 1 by U equals to 1 by F. If the surrounding medium is air, then the refractive index could be absolute refractive index of the lens. 1 by F equals to n minus 1 into 1 by R1 minus 1 by R2. This is the lens maker's formula. When lens is kept in air, where n is absolute refractive index, and this equation is called lens maker's formula. Note: always use sign convention while using any formula derived in the chapter, and the above formula can be used by any thin lens. The convex lens behaves as a converging lens if it is kept in a medium with refractive index less than the refractive index of the lens. It behaves like a diverging lens when it is kept in a transparent medium with greater refractive index than that of the lens. For example, an air bubble in water behaves like a diverging lens. Let us see an example for lens maker's formula. Example: what is the focal length of double concave lens kept in air with two spherical surfaces of radii r1 equals to 30 cm and r2 equals to 60 cm. Take refractive index of lens as n equals to 1.5. Solution. From the figure, using sign convention, we get r1 equals to minus 30 cm, r2 equals to 60 cm, and also given that n equals to 1.5, using 1 by f equals to n minus 1 into 1 by r1 minus 1 by r2. 1 by f equals to 1.5 minus 1 into 1 by minus 30 minus 1 by 60. Solving this, we get f equals to minus 120 centimeter. Here, minus indicates that the lens is divergent.